Kia ora, and welcome to a lesson on Level 2 networks, specifically minimum spanning tree. The way I'm going to show you to do the minimum spanning tree today is one of two main methods. Okay, we're going to be using an algorithm called Kruskal's algorithm. Okay, and the minimum spanning tree, in essence, is how can you connect all of these nodes together in the smallest amount of weight. So that could be distances, it could be time, it could be cost, depending on whatever these numbers here are representing. Okay. It doesn't need to create a nice loop or anything. It doesn't need to be like pretty like this. It can be any way of connecting all of the nodes together, like so, which connects all of the nodes. Okay, so all of these nodes are now connected. However, this might not be the minimum distance needed to connect all the nodes. So I'm going to show you the algorithm, and then we're going to use the algorithm. So Kruskal's algorithm, in basic, says select the shortest edge in your network. From there, you'll select the next shortest edge that doesn't create a loop. So a loop, for instance, on the diagram, would be if I've already got two of these edges selected, selecting this edge here would create a loop. Or a more complicated version of that could look, let me just work this one out. So if I had, there's no cross pattern here that I can use. Another loop could be just this. Well, that's another triangle loop, but I mean, let's have a look. Here we go. This is a loop. Okay, that would be another loop. So we can't create loops. Okay. Once you've selected the next shortest edge that doesn't create a loop, you carry on with step 2 until all nodes are connected connected to the minimum spanning tree. And once that's done, you add all the edges together to find the size of a minimum spanning tree. So we're going to use this as our example. So step 1, as mentioned, was select the shortest edge. So if I'm looking at this diagram, I'm looking at the edge with the smallest number. Okay, and sometimes there's more than one edge. In this case, we actually only have one, which is the 2 edge. So it's very important that you are careful looking around your diagram, finding where the smallest number is. So I've selected my first edge. I'm going to select the next smallest edge in this diagram, which doesn't create a loop. So there's actually the next two smallest numbers are either one of these three, doesn't matter which one I'm selecting. I'm going to select EF first, because they don't need to be all connected together. That would be a different algorithm called Prim's algorithm, where you continue on from other things you've selected, but we're using Kruskal's, which is just select any edge which is the next shortest, doesn't matter which one. So we've selected EF. And as I'm going along with these, I should actually be noting which edges I've selected. So I've selected BD, which is 2. I've then selected EF, which is 3. Okay. So the next shortest edge after this 3 would be the other 3. So I'm going to select that edge now. So selecting the edge CD. So CD equals 3. Sorry, can't write. There we go, 3. After that, the next shortest edge in my diagram would be this edge DE here, which is 4. So I select this 4. DE equals 4. Okay. And here we get to a point where the clause of which edge you select, the not creating a loop, is going to come in, because the next shortest edge in this diagram are the 5s. So it's either this 5 here, or this 5 here between DF. So either the 5 between BE or the 5 between DF. However, if I select the 5 between BE, it creates this loop here. There's no point connecting this edge here, because I can already go from B to E. Yes, it's a longer way of going from B to E in this case, because it's 6 long instead of 5 long. However, it's still a way of connecting B to E. And if you're talking about minimizing cost in a network, for instance, and you only care about connecting the nodes, you don't need to go along these extra edges, because you can just connect these to B to E together whilst also connecting B to D and E to D. Okay, so we're not going to select this 5, so I'm just going to put a cross through this 5, because it would create a loop. Same thing down here for the DF. If I selected the DF edge, it would create this loop here, so I'm not going to select it. So BE and DF were not selected, so I'm just going to write separately that BE was not selected and DF was not selected, so I can just keep track. After the 5s, the next number through is 6. There are 3 6s in this diagram. Again, some of these are creating loops. For instance, CF creates this loop. Okay, it creates this big old loop here, and BC creates a loop inside here. So I'm not going to select CF or BC. So CF, no, and BC is a no. However, selecting AB does not create a loop, so I'm going to select my AB and say I selected AB, which is 6. Okay, I've only got one node left to connect, so I've connected A, B, D, C, E, F. I just need now to connect G. So, oh sorry, I didn't cross off my 6s here, there we go. So looking at the next smallest edge, there's the AC7 here, which again creates a loop, not going to be necessary, so I'm going to cross it out. AC, no. And then the other 7 connecting to my G does not create a loop, so that is selected there, and I'm going to say EG equals 7. Okay, now looking at my diagram, all of my nodes are now connected to the minimum spanning tree. The way I know that is because if I look at any node, there is a green line coming off of it. Okay, and if all the nodes have a green line coming off of it, that means it is connected. So I don't need to continue this anymore. There was only one more edge to investigate, which is the 8 here. However, I don't need to investigate any more edges at all. So I've completed this third one, which is repeating step 2 until all nodes are connected to the minimum spanning tree. So I'm now going to do the last step, which is add all the edges together to find the size of the MST. And that might be a bit of a miswritten. It's add all the edges that have been selected together, not just all of the edges, otherwise that'd be a waste of time doing all this extra step. So I'm going to take all of these values here and add them together. So 2, add 3, add 3, add 4, add 6, add 7 is going to give me 25. So the minimum spanning tree is equal to 25, whatever my units may be. This is an abstract, but it could be a distance, so it could be 25 kilometers or 25 meters. It could be 25 minutes if I'm talking about the time it takes to travel from one location to another. It could be $25 if I'm talking about the cost of traveling from one location to another. So it could be anything to do with the context given. So this is what you need to be doing for achieved. It's drawing the network, highlighting the edges that you're going to select, saying which edges you selected, and finding out the total. If you're wanting to get merit for this, merit is gained by explaining what algorithm you used. So saying, to find the minimum spanning tree, I use Kruskal's algorithm. Kruskal's algorithm says to select the shortest edge, and then select the next shortest edge that doesn't create a loop, and continue doing this until all nodes are connected. Okay, so just explaining that you use Kruskal's algorithm, which is this method here. Okay, and writing that method down. That would be the merit criteria for this, and the inclusion of context as necessary. Okay, so that is the video on minimum spanning tree, and this will work for any network you are given, as long as you follow Kruskal's steps. Okay. Thank you for watching this video. If you're wanting more videos on networks, there's a video on traversability as well as a video on the shortest path using Dijkstra's algorithm. So please watch those two as well if you need to. Have a great day and bye.